Let's have a look at this example here then. Again, it's in the textbook. This time it's a definite integral, so we're going to end up with an answer, because we can put those limits in. The pi over 6 is telling me immediately that I'm working in radians, so I know that when I do put the limits in at the end, I'm going to have to be working in radians, so I check that on the calculator. I'll certainly be thinking about, and I might not write this, but I'll certainly be thinking about this integral as being the same as 24. I could take the 24 outside the integral between 0 and pi over 6. Any constant can come out. And sine to the power 5 theta, of course, means sine theta to the power 5 times the cosine of theta to theta. So that's actually another way of writing that integral, or certainly think about it anyway, because that will give me a very strong clue as to what I'm going to call u. So I'm going to let u equal sine theta. If I integrate sine theta, I get minus cos theta. I'm doing this in my head, okay? So I'm thinking, by letting u equal sine theta, I've not got rid of the original variable because I've still got cos theta. So somehow that's going to have to disappear. But I remember that if I differentiate sine theta, I'm going to get cos theta. And so that cos theta is going to go underneath, and that cos theta will cancel with this cos theta. So it is going to work. Remember, it only works if the original variable disappears. So I know it will work. I'm inspecting it even before I start it to check it's going to work. I look at that and say somehow that's got to disappear. Oh yes, when I differentiate that it will disappear. If that cos theta wasn't there and I was just asked to integrate sine to the power 5 theta, I'd have to think of another technique. And we'll perhaps look at that. That actually would be a trigonometric substitution. So we know we're going to be okay, so let's actually do it. So let's let u equal sine theta. So I'm going to differentiate that. Du by d theta is cos theta. So rearranging for d theta, that's going to equal du over cos theta. See the same sorts of steps every time. So now I'm going to make the substitutions. I'm going to replace sine theta with u, and I'm going to replace d theta with that. So the original integral, 24 sine to the power 5 theta cos theta d theta can be rewritten as, we've got the limits, 0 and pi over 6, and it will be 24 integral between 0 and pi over 6 u to the 5 du times cos theta du over cos theta, making the substitutions, and that's theta there. The cos thetas cancel as we predicted. So it equals 24 integral between 0 and pi over 6 u to the 5 du, which is a standard integral. Actually turns out to be the one we've used already. Just add 1 to the power, divide by the new power. Let's see. Oh no, not plus c, because it's a definite integral, and so between 0 and pi over 6. Six is going to 24 4 times. That 4 can come outside the square bracket, so we can simplify that quite a lot and call that 4 times u to the 6 between 0 and pi over 6. And then we replace u with what it was originally, which is sine theta. For sine to the 6th of theta between 0 and pi over 6. If I'm putting these into brackets, these limits, I would actually think of it as sine theta to the power 6. So I'd use the power 6 button on the calculator. So that's going to equal 4 times, putting the limits in, sine theta, or sine pi over 6 to the power 6, minus the sine of 0 to the power 6. So that's putting the limits in. We know that the sine of 0 is picture of sine wave. Sine of 0 is drew a sine wave, it would look like this. So the sine of 0 is 0. So I know this bit is 0. So I don't need to worry about that bit. The answer is just going to be 4 times the sine of pi over 6 to the power 6. And that's what I would do in my calculator. Equals 1 over 16. So to quickly recap, the substitution this time is again what's inside the bracket, thinking about this as being rewritten like that. Then that makes that fairly obvious what we're going to let u equal to. It's only going to work if when I make the substitution this cos theta disappears, and so differentiating sine theta means we get cos theta, so it is going to work. And then we just go through it, putting in the substitutions, checking we're in radians, and then working out the definite integral to get that answer. Okay. I did say I was going to sort of ask you to check some of these, and you could take any of these examples and do it using a numerical method. Between this last one, for example, you could use Simpson's rule that we use for the area under a curve, so you could try this particular one using Simpson's rule and see if you get the same answer, near enough, 1 over 16 or whatever that is as a decimal. Because that's the sort of thing that might happen in the real life.